Welcome. Today we will be discussing section 3.3, polar coordinates, as well as some conversions with examples. So, polar coordinates are an ordered pair written as such, r and theta, where x is equal to r cosine theta, y is equal to r sine theta, at where x and y are our rectangular coordinates, which means the one that you are probably most familiar with. And we also have that r is equal to the square root of x squared plus y squared. And theta is equal to the sine of y times cosine inverse of x over square root x squared plus y squared. So in other words, we have, for any point, we have an x distance from the origin, we have a y distance from the origin. Well, r is the total distance from the origin, the Euclidean distance, to be precise. And then theta just describes the direction that the point is from the origin. So if I was to draw a graph, we can think of this as if I had a point here, I could call this some positive x, and then this distance is some positive y. Well, and we just call this x and y. In the rectangular coordinate system, this is what we're used to. For polar coordinates, it instead goes, okay, instead of that, we're going to go, how far out are we from the origin? Well, that is the radius r of some, and why it's r is because we can think of, like, if we were to draw a circle, this is the radius of what circle contains this point. And then we want to be precise on the point. We want one point, not an entire circle. And we go, hey, what's our angle from the positive x-axis? And that will get us our point. Because every angle that we get, because we have fixed our distance to some r, will be at some point along the circle. Which point? Oh, we want this one. That's a particular theta. And as we've seen from the previous video, we're able to get the measure of this r by taking the x squared plus y squared and taking the square root of it. And then the y, or sorry, the theta, we're able to get by matching the sine of y times cosine inverse of x over square root of x squared plus y squared, or the magnitude of, you can think of like a vector from the origin to this point. So there is a conversion to go from rectangular coordinates to polar coordinates and vice versa. So we're going to focus on rectangular to polar conversion. So the rules are if x, y is equal to 0, 0. In other words, if we're at the origin, then r is equal to 0 and theta is equal to any number. It's basically within all reals. So theta of 0, theta of 40, it doesn't matter. And 40 degrees or 40 radians, it doesn't matter. Because if we think about a circle with 0 radius, it's just a point. It doesn't have what direction. It's similar to kind of like the unit vectors of, or any vector of distance 0, it doesn't have a direction because it could go in any direction. It doesn't matter which direction you're facing because you're not going anywhere. So if we don't have that, if x, y does not equal 0, 0, so literally any other point, then we have two conditions. We'll have square root of x squared plus y squared, and we'll have theta being equal to, or theta plus 2 pi n. This is if r is greater than 0. And we'll have negative square root x squared plus y squared. And we'll have theta plus pi plus 2 pi n. This is if r is less than 0. So what do I mean by that? Let's go back to this example. Is that my r is, so if I state that my r is greater than 0, then my distance is positive. But if I set a negative r, you can think of that as like picking a direction and then walking backwards. Well, what am I really doing? I'm just turning around and going that direction. So if I have a negative, if I'm still going like this direction, but I have a negative r, I'm really going this direction. Well, how do I accommodate from this theta to get to this angle? Well, this is just a 180-degree rotation, or a pi radians rotation. Hence, if we have a negative r, we just add a pi to it. And then if we have a negative r, we're going to add a negative to the magnitude, or square root of x squared plus y squared, because then that makes it positive. So now we have a positive distance and an angle to match going the positive direction. Again, you can think of it as walking backwards is the same as starting in the same position, turning around, and then walking forwards. We want to standardize distance being positive or our radius being positive, and so that's why we have this mechanism here. This will be your check on learning, is to write down these rules for rectangular to polar conversion. Again, that will be your check on learning for this video. So what are some examples we can do? Well, let P be equal to -1 square root 3. So in other words, we're going to start with a point in the rectangular plane. And now we want to convert this to polar coordinates. So we want to find polar coordinate. And I'm going to amend this statement and say I want to find all polar coordinates. Why do I say all? Well, we have this n here. And this n shows us that we can hit the same place multiple times just by spinning around the circle one complete rotation. So we want to first find the distance. So step one, we want to find r. So r is equal to square root of -1 squared plus square root 3 squared, and we get 1 plus 3, 4. So we're going to take the square root of 4, which is plus or minus 2. We're taking plus or minus because now we're dealing with the coordinate system. We're not exactly sure where we land. And this is because our theta is restricted in the domain of cosine inverse. So, and we'll explore this concept in a second. So now we want to, step 2 is find theta. And so what we're going to do is theta equals the positive cosine inverse of -1 half, which equals 2 pi over 3. And why did I write down a positive over here? Is because I look at my y coordinate and I see that this is positive, so I'm going to have positive cosine inverse. So now we have two situations. If my radius is equal to 2, then I have 2 is my first entry in this ordered pair, but my theta is going to be 2 pi over 3 plus 2 pi n. Again, that is symbolizing that I'm going a positive distance, and so I'm just going to take my theta. This is where it lands. This is the direction I'm going, but I might have spun around a few times before I started going that direction. If r is equal to -2, then we have -2, and we look at our rule, we have our theta, 2 pi over 3 plus pi plus 2 pi n, and we can simplify this and rewrite this as, so this is positive 2. We want a positive 2 because we're going to times it by a negative. And we have, this is 3 pi over 3, so we're going to have 5 pi over 3 plus 2 pi n. So that is our total answer. That contains all points that we could be. And if you went and you plotted this out, you would see that we have a circle of radius 2. That's what this r is 2 and -2 is. So that's 1, this is 2. We're going to have a circle. And then what direction? Well, 2 pi over 3. So if this is pi over 3, this is 2 pi over 3. So right here, this is our point, which that matches -1 and square root 3, we can think of -1 and then positive square root 3. But then for this point, we have 5 pi over 3. So we have 3 pi over 3. And then we're going another 2 pi over 3. So that would be here. And we get this answer because it, again, has a we're instead going to we instead can think of it, instead of starting at this angle, because of the pi, we started at this angle, which then if we go 5 pi over 3, we'll end up here. And why are we starting here? Well, think of it as that because of the negative, we started going a distance of 2, and then we went to our angle. Well, here we traveled -2, and now we have to go our angle, if that makes sense. So here we traveled out 2, and then we spin 2 pi over 3. With a -2, we travel first -2 distance, and then we spin 5 pi over 3. And we land on the same point. That's why both these answers exist. Okay. So now we're going to work on some equation conversions. So we want to be able to have a equation in the rectangular coordinate system and put it into the polar coordinate system and vice versa. So when we go from rectangular to polar, we want to have x equal r cosine of theta and y equal r sine of theta. If we're going from polar to rectangular, we want to have a few more steps. So the first step is cosine of x over r, cosine of theta is equal to x over r, and sine theta is equal to y over r. And we want to replace these instances. So wherever I see an x, I want to put in r cosine theta. Wherever I see a y, I want to put in r sine theta. In the polar to rectangular coordinate system conversion, we want to generate and break everything down into cosines and sines, anything with variables, with theta specifically, and transfer them back into x and r's. Well, r we know is square root of x squared plus y squared. So really we're putting that into here. But the next step is r squared equals x squared plus y squared, which implies that we can take the square root. So r is equal to plus or minus square root x squared plus y squared. So something to note is that there's a chance that R could be 0 at some instance, which then we have to investigate that and plug and check the case on whether R is 0, just to make sure that our theta doesn't diverge, or cosine theta doesn't diverge, I should say. So let's find another example. And let's have 3x minus 4y equals 5. We want to convert this to polar. So we start by finding our x and saying that is 3 times r cosine theta minus 4. What's our y? It is r sine theta, and this equals 5. And we can simplify a little bit. We can pull out an r. So we can have r is equal to 3 cosine, sorry, r times 3 cosine of theta minus 4 sine theta equals 5. And 3 cosine theta, negative 4 sine theta. There is no theta that would make this equal to 0, so we can divide by it, and we have r is equal to 5 divided by 3 cosine theta minus 4 sine theta. And if this fact is, to check on this fact, we can simply go 3 cosine theta minus 4 sine theta. We want them to be equal to each other to get 0. Does this happen? Well, if I divide by cosine theta, I have 3/4 equals sine theta over cosine theta, which is tangent theta. And so when I take this, I have tangent theta, or tangent inverse of 3/4 equaling theta. So I can simply state that whenever theta doesn't equal this, it works out. And we get this equation. This equation when theta does not equal tangent inverse of 3/4. Yeah. So that would be our answer. Let's go through another example. Let's keep that. We have convert r equals 6 cosine theta plus 14 sine theta, and we want to convert this to rectangular coordinates. So we first go, all right, let's suppose r does not equal 0. Then we can do these steps. So let's first put in cosine of theta is x over r. So we're going to have r is equal to 6 times x divided by r plus 14 times y over r. And again, I have it being over r because we're assuming r is not 0, which then we can times by r to the other side. We get r squared is equal to 6x plus 14y. Well, what is r squared? That is x squared plus y squared. So we're going to have x squared plus y squared equals 6x plus 14y. And we can leave it like this. We could simplify and like move all the x's to one side and all the y's to the other. But if we leave it like this, in implicit form, this is fine. So now we have to go this step, r could have been 0. So what if, so we're going to suppose if r equals 0. Well, then we have 0 equals 6 cosine of theta plus 14 sine theta. Well, we subtract 1 across, so let's subtract the 6 cosine theta, so we get negative 6 cosine theta is equal to 14 sine theta. We can divide by cosine theta to each side, but let's also divide by 14, and we get negative 3/7 is equal to tangent of theta. We take tangent inverse of each side, and we get theta is equal to tangent inverse of negative 3/7. So what this means is that whenever we're at this angle, we'll have a radius of 0. And so all that we have to do is just disallow this, and that whenever, so we can say that if theta equals tangent inverse of negative 3/7, then no solution. So we have this equation, but we're going to take out all of these instances. And specifically what we can see with this is if we evaluate this, what will happen is when we plug this theta into these equations, depending on which instance you use, because we have a lot of thetas that could be this answer, we'll have a positive or negative sign, and that's where our issues come into play. Or we'll basically have a division by 0. So in summary, when we're looking at equation conversions, we can convert to the other side of it, but we have to be careful that what we have, we're not dividing by 0. That is all content for this video. Thank you for watching. Have a great day.